So, so far what we learned was about vectors. So can somebody tell me what a vector is? Yes.
It's a line with direction and magnitude.
Okay. Examples of vectors. What examples do we have? Physical examples. Yes.
65 miles per hour going northwest.
Okay. Anything else? Yeah. All right. Like? Weight. Right. So what we learned basically was physical entities. So the question is, what is vector good for? And the whole idea really is to show you that what you have already learned in algebra, in trig, now we're going to represent it in a vector form, and we're also going to show you how simple it is to do many of the manipulations that you did in the past. So one of them was, let's pass this, a two-link robot, right? So in a two-link robot, why is it? Okay. So in a two-link robot, we were looking at the position at the tip of the robot, which was really based on that hinge in the middle and the movement of that hinge. So the question is, how do we find out the location of this point P relative to the XY coordinates? So the first thing I'm showing you is, again, by physical, observation, by looking at it. So if I'm looking at the position of that point, and based on what this vector and that vector is, it's very simple, right? I want to know the XY coordinate of that point. So when I'm looking at that point, I can easily deduce that the x coordinate of that point simply is a summation of the x coordinates of point 1 and 2. Do you agree? Can somebody tell me why? You agree, so let's see why. Yeah. Forget about the angle. Just physically looking at it. Right. So just by physically looking at it, regardless of whether that point goes up and down this line, the position on the x coordinate is going to remain the same. Right? It's going to remain the same. The only thing that happens, of course, is that point might actually go up and down because we're pressing against it or pulling it. So this is just a physical observation. That the same thing. Can we do the same thing for the y coordinate? And the y coordinates would be what? Yeah. Right, exactly. Oh, this one. So when we are looking at these two, which are two vectors, that will tell us the addition of two vectors simply is the addition of x and y coordinates. So now, looking at it from a vector point of view. In a vector point of view, when I want to show the new vector, which is vector P, the new vector, which is vector P, simply is a summation of two vectors, P1 and P2. So, looking at the P1 and P2, what is P1? In vector format. You remember? In the Cartesian coordinate system, we used something. Do you remember what it was? Yeah.
That's the I hat,
Right. What is I hat?
pointing to the X direction.
It's a unit vector in the X direction, right? A unit vector. Does that have a physical meaning? Does that have a units? Is it in meters? Is it in centimeters? What is it? Yeah. Exactly. Basically, it's a dimensionless unit vector because, in fact, your dimensions do not come from I and j. Your dimensions come from px and py. So if you're working with meters, that would be meters. But the I and j do not have it. Why do we show it this way? Because we're showing it that the px actually is a scalar quantity. Scalar quantity. Have you heard that term before? Scalar basically means it has a magnitude but no direction. The difference between a scalar and a vector is exactly that. So pxi and pyj. Now, we also know that the vector p or p1. So if I'm looking at the point 1, p1, and I want to use the same terminology, what is p1 equal to? P1 as a vector. Look at the diagram. Look at the diagram and tell me. What is this? And this. Px1 and Py1, right? That's the xy coordinate of point 1. So if I want to describe P1 in terms of x and y coordinate and using the same Cartesian coordinate system, how do I describe P1? Come on, take a crack at it. Yeah. Don't go that far. I just said in the Cartesian coordinate system. Yes. You want to say that? Right. So you tried. It's basically px1i plus py1j. Do you understand that? Okay. So go back to here again. So say the point P. Where is point P? P is here, right here. This point P. Okay? This is the vector. Okay? We are describing point P as the x and the y coordinate. This is the px right here times unit vector I, and this is py right here at unit j. Right? So describing in the Cartesian coordinate system, we say P as a vector is equal to the x coordinate of that P, which is Px, and then times unit vector I plus Py times unit vector j. Do you understand this part? Yes. The I and j are vectors. The px and py are scalars. All right? That's why we are using I and j, because we are showing it as a direction cosine, basically directions in the x and y direction. So if I want to use the same terminology for this point, what do? I say P1 is equal to P x1 times the unit vector plus py1 times the unit vector. Do you understand? So basically that's what we have. P1 is px1i plus py, and for point 2, the same terminology. Questions? Any questions? Thanks. In all of this, I'm referring to it as a position vector. When we say position vector, because we want to know where in space or in the xy coordinate that position is. If I simply give it as an x and y, I know the location, but I do not know the direction. So for displacement purposes, as we said, displacement is a vector. Therefore, we need to know the direction. Any questions? So now I know P1 and P2, but we also know that this position is a summation of two vectors. Do you remember when you were doing the two-link robot, when you wanted to find the location of that tip, what you had to do? You had to do a lot of cosine interactions and summations and so angles and so forth. We're just simplifying it through the vector. So the vector is saying that the new vector, which is the location of this two-link robot, is the location of the first position plus the location of the second position. Any questions? So let's go back to the diagram again. So what did I do over here? We say that vector P is based on the two positions of 1 and 2, but at the same time is described as pxi and pyj. P is this location. This and this relates to the first position, and this relates to the second position. So what we basically did in the equation that we had before, we factorize the unit vector I. Okay? Do you remember that? P was equal to px1i plus py1j plus px2i plus py2j. Both of them has I and j. We factorize I, and that's why we now have px1 plus px2. So physically, what does that mean? Physically, we are simply saying that the x-coordinate of that position simply is the summation of these two. And the y is the summation of these two. So simply comparing these two together, px, which is the position x-coordinate of the new vector, is the summation of these two numbers. And again, it comes from the comparing these two. Any questions so far? So if I'm looking at these two, what is py equal to? Yes. There you are. Which is basically the same conclusion that we made when we were physically looking at the problem. Simply adding the two vectors, adding the two vectors amount to adding the xy coordinates. All right, so now we want to get some values here. Now we got it as a vector. Now I want to actually go to the problem itself and find out what these values are. Number one is I want to find out what is px1. How do I find px1? How do I find px1? The x coordinate of point 1, and this is point 1. How do I find the x coordinate of point 1? Yes?
P1 cosine of 45 degrees.
Absolutely correct. There you are. And the same thing goes with py1. Do you agree with that? So we've simply found this and this based on this, which is 1 over square root of 2. Can somebody tell me what is 1 square root of 2 times 1 square root of 2? Why is it equal to half? How? Because it becomes 1 over square root of 4. Square root of 4 is 2, so it's 1/2. So if I want to show it in the Cartesian coordinate systems, that's what we have. So I found the Cartesian representation of point 1. So what should I do for point 2? Yes. Same thing. So same thing means what? What is the px2? Of what angle? 30 degrees. And this is where the 30 degree is. In that area, somebody tell me what is py2 equal to? What of 30 degree? Sine 30 degrees. Right, exactly. All right? So if I want to represent point 2 in a Cartesian coordinate system, what do I do? What is P2 equal to? Yes. Py1 plus Py2, no. I want to say, show me first of all, Py1, Py2, it's the y coordinates of two different points. So I want to show it as a vector. This is point 2 I'm talking about. See how we did this? How did we do this? Yes. Excellent. That's exactly what we do. There you are. Can you explain why?
Me?
Yeah.
Let me explain. Oh, because it's just like that.
Exactly, because you're only putting the xy coordinate of the end of the vector, and then you multiply it by the unit vectors I and j. Don't be shy if you don't understand, because I want you to really understand this before we move on. Yes?
Would you, for P2, would you add the x values together from both P1 and P2 to get like the coordinate?
No. Because what you're effectively doing in that case, you're actually giving me the location of the end of the two-link vector. You're giving me that. I'm not interested in that. The whole exercise is telling you that eventually I'm interested at the end of that two-link robot. But they have individual entities. So when you're looking at one vector on their own, you only look at the x-coordinates relative to the end, both ends. So as if the origin was at the beginning of that vector. That's why we go that way. But they kind of sum it up. Because when we say px2 is equal to whatever it came out as the 0.433 meters, is only talking about this little link underneath. We're not talking about the x-coordinate. We're only talking about scalar quantity. Okay? So the next thing is that we want to find out P. So what should I do here? Yes. That's right. So now we have the vector representation of both points P1 and P2. And all we have to do is just replace it in that formula. How do we do this? Can somebody give me the answer? Yes. Right, so we get i's together and j's together as if we are factorizing I and j. So I'm adding this and this to get the term for the I, and I'm adding this and this to get the term for j. Which effectively is the x and y coordinate of the end of that two-link robot. So the next thing is, of course, this is the Cartesian representation of the vector. Now I want to show it in the polar term. Do you remember the polar form of a vector? What did we need for a polar representation of a vector? Yes. Yes, P and the angle. P and the angle. How do I find P here? Huh? No, it's not already there. You got to calculate it. You're right. Yes. So now we know the length of that vector. 1.197. And of course, don't forget, you need to put the units, meter. Now, what else do we need? Yes. Angle. How do we find that angle? Okay. Py over px. Is that how we find the angle? Yes, back there? Arctan, yes, yes. Arctan of 2, as I said, because arctan of 2 take into consideration the quadrants. And that's the angle. So now we have the vector, the length of the vector, and we also have the angle that it makes with the positive x direction. So if I want to show it in a polar form, how do I show it? Yes?
P equals 1.197 angle 38.79.
Absolutely right. And I'm so pleased because that means you've understood it so far. Very good. So far, so good? So now, just imagine all the trigonometric manipulation that you did last week. We just did it very simply through a vector summation. You are already in your sophomore year. Can you believe it? With this problem, you are already in your sophomore year. So you're already, only 3 years to graduate. Yes?
I've seen you do it two different ways for the units.
Uh-huh.
The meters after the degrees, or do you want it after 1.197?
I put it here because that is, for this one, the meter comes here. Because the degree is for the other one. So now let's do an actual problem. All right. So a ship travels 200 miles at 45 degrees north of east. North of east. Okay? 45 degrees north of east. And then 300 miles due east. Now we want to find out the position of the ship. Now you all know, oh, this is a piece of cake. I know this. This is vector. All I have to do is draw the diagram. (45° north of east, and so that's 45 degrees, and 300 miles east, which means the angle is horizontal to x-axis. Who disagrees with me? Well, nobody, because it's already there, right? So if I want to find out the position of this, and I want to represent it in a vector form, I would say P bar or vector is equal to yeah, P1 squared plus P2 squared square root. Is that correct? No. So what is it then? Yeah, but I said I want to show it in a vector form. What is P equal to? That's right. We just did it. P1 bar plus P2 bar. You're kind of speaking a little bit ahead of yourself because you already know what you need to find out, which is great because that means, you get it. So I want to find out P1 plus P2, right? So going here, P1 plus P2, what is the first thing I got to do? Think about that, location, which was like this, going this way, 45 degrees, and going that way. So this was 1, this was 2, and that's what you want to find, right? So the first thing is find out P1. What is P1 equal to? Yes. 200? Is P1 bar is equal to 200? No. What is P1 bar equal to? P1 bar is equal to Px1 I plus Py1 j. Do you agree? Right. So we want to find out what is Px1. What is Px1? Yes. Right. P1 is 200 cosine of 45. What about Py1? There you are. Boy, is this easy. Which basically gives you P1 as 141.4 I plus 141.4 J miles. Don't forget the units, miles. So, we've done this. What else do we need? Yes. We need P2. Can you tell me what P2 is? Uh-huh. You don't need to be in this class now. You can just leave. Right? Easy. Who agrees with her? Nobody? Then you got to stay. Sorry. So, we found P1. We found P2 bar. What do we need to do? Yes. Add them together. Right. The easy part. So, if I want to add this together, can somebody give me the answer? Yes.
441.4 I plus 141.4 J.
This is kids play, right? So easy. Now you can actually be in Navy, because now you can actually find the location of your ship and where you're located relative to your origin. So now I found this. I want to show it in a polar form. For the polar form, what do I need? What do I need? Yes. P and angle, right. Or simply put, magnitude and direction. Magnitude and direction. What does a vector have? Magnitude and direction, right. So if I want to find out the magnitude, which in this case is P, what do? I have the x and y coordinates, right? The scalar quantity. And I find the square root of that. So now I want to find the direction. Temple T at the end, over there. What is the angle? Yes. Come on, don't be shy. Speak up. Right, it's not 8 tan squared, it's 8 tan 2. Right, 8 tan 2 of Py, which is 144, divided by 441, 17.76 degrees. So if I want to show this vector in a polar form, how do I write it? How do I find it? Yes. Right. Doesn't matter, you know, we can put miles before or after, because everybody knows the other one is angle. All right, so far so good? So now we want to do something else. Now we want to talk about relativity. And relativity, we're not talking about Einstein theory, which of course is related to that. But relativity always means that while you are talking about your position, your velocity, your acceleration, you must have a reference point. The reference point is not the center of the earth. The reference point is somewhere. And then when you are comparing yourself, or when you are describing your physical situation, you want to describe it relative to a reference point. And in that case, what we call a relative velocity. Now, relative velocity, you will see it in dynamics. And for example, if you are flying in 100 mile per hour, and I am flying 200 mile per hour in the same direction as you are, although my velocity is 200 mile per hour, say going east, but compared to you, my relative velocity is only 100, because you're going at 100, I'm going at 200, both of us are moving, so relative to you, I'm only as if I'm going at 100 miles per hour. Do you understand that? As if when you are running together, your relative distance could be 0. But regarding to a reference point, would be something else. So let's do an example. In this example, we have a airplane that flies at a speed of 100 miles per hour, heading 30 degrees south of east. If the velocity of the wind is 20 miles per hour due west, determine the resultant velocity of the plane with respect to the ground. Can somebody tell me if the relative velocity of this plane is it more than 100 miles per hour or less than 100 miles per hour? Yes. Less. Why? Right, because the wind is opposing it. Just, so there comes the logic that we've been talking about, the logic of engineering. So if I draw it, this is what I get. I get the initial, this is the initial position, but then we have the wind, which is opposing it. And what I want to find out is velocity of the plane. Is this a vector addition? Yes. We don't always have to have vectors like this in order to add. We could have actually vector like this and then add. Okay? But one is subtracting the other one. And that's exactly what we do over here. Do you understand this? So, in this case, we have this value, which is the initial position or velocity of the plane, and then we have this, and we want to find out what this is. So in order to do this, what do I need to do? It's a vector addition. What do I need to do? I need to define these two vectors. I need to define this, and I need to define this. So the first one is, what is V bar PA, which is this one. What is that equal to? Is it 100? I'm talking about the vector representation. I'm not talking about the scalar quantity. What is that equal to? Come on, it's all right. Yes. Vx1I, don't forget I and j, plus Vy1j. So Vx1I is what? How do I find it? Is this, right? Yes? What is that equal to? See that angle, 30 degree? I want to find out what this is, this part. How do I find it? Yes. 100 cosine of 30. So, huh?
Would it be negative 30?
Would it be negative 30? Yeah, does it matter? No. Cosine of 30 and cosine of minus 30 are the same. But you are right. It is minus 30 because we always measure it in the positive direction. And the same thing goes with the y direction. 100 sine of 30. Is that negative or positive? Negative and positive. Everybody's saying negative, positive. So which one? Negative or positive? It is negative here. Why is it negative? Because it is in the negative direction. This is positive. This is negative. Okay? So that is the vector representation of the velocity of the plane. Is that enough? Is that enough? No, because I need to represent this, VA. What is VA is equal to? The vector representation of this vector. What is that equal to in I and J? 20I minus 0J. Do you agree? Do you see the direction? Negative, right. Any questions so far? So what do I do now? I want to find out this, right? What do I do now? Yes? Yeah, it's a vector summation. All right? Which simply results to this. So I have represented in a Cartesian system. If I want to show it in a polar system, what do? How do I find the angle? Go on. Arctan of? Right. Which is minus 36.9 degree. Does that physically make sense? Yes, look, it is a negative direction. Now, if you wanted to use your old system, you could have used the laws of cosines and sines, right? In that triangle, cosines and sines. Look, the same thing that you did in the trig part. See? You get the same answer. In this case, of course, we had to find alpha. In alpha, what do? Use the sines. Sine of alpha and the the side in front of it, sine of 30, and the sine in front of it, and that's where you find sine of alpha, which is alpha is 6.896. Once we find alpha, we add it to that 30 degree, and that's what your angle would be. Do you see this? So I use the vector system, I'm using the trig system, and I'm coming up with the same answer. Okay? Any questions? We'll cover the rest of it, I guess, sometime next week. Look at the your blackboard. Yeah, we'll tell you where you're supposed to go.